Okay, hello everyone. Welcome to our lecture today. My name is Alicia, and I'm going to be taking you guys through our 3 and 4 physics lecture. So, today's lecture is provided by ATAR Notes, who create resources for all high school students. ATAR Notes provides study notes, lectures, discussions, videos, newsletters, the ATAR calculator articles, and heaps more. And we also provide a tutoring service by recent Year 12 graduates, study guides, and Ed Unlimited. So, let's get into our lecture for today. So, let's get started with a quick recap of what today's lecture is going to entail, what content we're going to go over, and what the structure is. So we have a 2-hour recorded lecture, which means that you can pause it at any time if you need to take a note, or if you didn't understand a particular thing and you want to replay it. Or it also means you can watch the lecture at any time, even if it's not the time that it's being live streamed at. So there is also a live chat. So please feel free to ask any questions about the content, if there's a particular example that we did, a particular concept you didn't understand, or even something from previous topics, say in Unit 3 that we're not covering today, or something from Year 11, or even something from another subject. Anything about studying, study tips, balancing all of your subjects, externals, anything like that, or even uni, moving out, anything like that. So, the content that we're going to be covering today is special relativity, and then quantum theory and the standard model. So this is our Unit 4 content. We're doing all of Unit 4 today. Alright? So, these are the goals of today's lecture. So most schools will be finishing up Unit 4 content by now and kind of heading towards mocks and going through revision for your externals, but you should have mostly finished the actual content. So what we're going to be doing today is revising Unit 4 content and preparing for your mocks. We're going to go as in-depth as time allows, so make sure you have something to take notes with. We're going to go over a few worked examples, and then any tips that I have for particular content, things to look out for, common mistakes, common exam questions, even if there's a particular way to kind of remember a certain bit of content, or anything like that. And I've been where you are, so I know the pain very well. A little bit about me. So I graduated in 2021 with an ATAR of 99.55. I went to a small rural school, and then I'm currently studying a dual degree in law and economics at UQ, and I'm living in Brisbane. So physics was one of my favorite subjects in Year 12. I kind of find that I liked the maths and science subjects more. I didn't do biology or chemistry. So physics really was my only science, and because I kind of liked maths so much, it was really fun to kind of apply the maths in a situation where it wasn't too complicated, and the main part of it was actually like the interesting kind of concepts. Of course, I wouldn't always say that. Sometimes it got a bit hard, especially with electromagnetism. I did not like electromagnetism. It was just too difficult. But special relativity was especially interesting because it's not even much about maths. It's mostly just kind of cool concepts. As opposed to what we do at the beginning of Unit 3 when we're doing like projectile motion, inclined planes, gravity, all that kind of stuff, where it's a lithy bit more mathsy, but the concepts aren't really as interesting. So yeah, Unit 4 really was a highlight, but physics was one of my favorite subjects. You might be able to tell as we're going through the lecture today. As I said, maths was my favorite subject, so I did methods and specialist. Um, so I might use like some more, I guess, complicated algebra or something like that, but I'll always let you guys know what you're expected to know, and then how you can kind of get around particular maths things, or if there's a particular thing you need to learn if you're in general maths and not in methods. Alright, again, if you have any other questions at all about myself or anything like that, please feel free to pop them in the live chat. But with all of that being said, let's get on to special relativity. So, here is a quick snip of the syllabus. So, this is all of the content that you need to be able to know for special relativity. So, it would be a really good idea to kind of add these to your notes, or personally, what I did, especially for physics, and what I imagine would also be useful for other science subjects, is to make a list of external notes on your laptop, typed up, where you kind of copy and paste the syllabus, and put your notes under each syllabus dot point. And this way you really understand everything on the syllabus. You really only know what you specifically need to know, and you're making sure that you're not missing out on anything. Otherwise, it's kind of really easy to kind of like accidentally skip a chapter in your textbook or something like that. If you have your syllabus dot points on your notes, it really ensures that you're not going to forget anything. Alright, so quick overview of what you need to know for special relativity. You need to understand the presence of muons in the atmosphere as an example of natural phenomena that cannot be explained by Newtonian physics. You need to be able to define all of these terms. So as you can see, all the terms you need to define are in gray italics underlined. And then after all of these terms you need to be able to remember the definitions of. There are a few kind of solve dot points. So you need to be able to solve problems involving time dilation, length contraction, and relativistic momentum. And you also need to be able to describe time dilation and length contraction. And then you also need to be able to recall the mass-energy equivalence relationship, explain the universal speed limit, and also explain our three paradoxes. So this is the content that we're going to be going over today. So, let's start with muons. So, in our syllabus, it states that we need to be able to describe the presence of muons in the atmosphere as an example of a case where normal Newtonian physics does not apply. So, let's go over what is happening with the muons, why they're in the atmosphere, and why it shows us that Newtonian physics does not apply. So, Newton assumed, Newtonian physics assumed that space and time are constant, that they're uniform and straight. This is a kind of a pretty, I guess, commonsensical assumption to make, right? Space and time are constant, right? So, this is what Newtonian physics is. Space and time are constant, uniform, and straight. Let's get on to what's happening with the muons. So muons are an unstable particle. They're a very, very small particle. We actually learn more about what muons are when we get into the standard model. But they're an unstable particle created when high energy cosmic rays interact with the nuclei of oxygen atoms 15 kilometers above the surface of the Earth. Right? And they have a very, very small lifetime, about 2.196 microseconds. So essentially the situation we have so far is we have a bunch of these tiny little muons, And they're created in the atmosphere because of these cosmic rays. They create them in the atmosphere, and they're really, really tiny. They also move at 99.97% the speed of light, so they travel like super fast. Right? These tiny, tiny particles move super fast. They're created 15 kilometers above the surface of the Earth. This is what we have so far. So, Newton would tell us that the muon's life will end 8.41 kilometers above the surface of the Earth, right? So they're traveling really fast, but they have a tiny, tiny lifetime. So they're not going to get to the surface of the Earth. They're not even going to get halfway there from where they were created. And after about 10 lifetimes, there's going to be no muons. So according to Newton, we should really not be able to see any muons, maybe a few, but barely any muons on the surface of the Earth. However, we actually detect a lot of muons on the surface of the Earth, and they actually live 22.8 times more or longer than predicted. So they existed for a longer time period than they should have. Right? So, our situation is we have lots of tiny, tiny particles, muons, created 15 kilometers above the surface of the Earth. They move really, really fast, but they also have a very, very short lifespan. According to Newtonian physics, which says that time and space are uniform and straight and constant, the muons should not be getting to the surface of the Earth. However, we measure a lot of muons on the surface of the Earth, which tells us that Newtonian physics does not apply. Because, evidently, for the muons, the time and space were not constant, uniform, or straight. Something happened to time and space, and something changed the time and space to allow all of these muons get to the surface of the Earth. When according, if space and time were constant, they would not have been able to get there. Alright? In a little bit, we're going to get into what exactly happened to the space and time. But for the moment, let's get on to our next syllabus dot point, which is a few of our defining terms dot points. So the first one is reference frames. So special relativity is based on the relativistic nature of motion. So any motion that is observed is relative to the reference frame of the observer, right? What this essentially tells us is that motion is relative, and this is a pretty solid and integral part of the actual special relativity theory that we're studying. Motion is relative, right? If I am standing on the side of the road and you drive past on the road, you're moving relative to me because in my perspective, you're driving past, and in your perspective, I'm moving relative to you because what you're seeing is you're seeing you stay still and the road and me move past you. Because in your perspective, the car is staying still. Even though I guess logically, you know that you're the one driving. In your perspective, the car is still and the road is moving relative to you. So, what we can say is that a frame of reference is an abstract coordinate system and a set of physical reference points defined by the observer, used for observation and description of physical phenomena. So, this definition kind of sounds like a big, long jumble of words. What I'd recommend is for you to go and memorize the definition provided by QCEE on the syllabus. So obviously, if you find the syllabus online, you can just Control F reference frame, find the definition in the glossary at the end, copy paste that into your notes and memorize that one, because that definition is the one that you're going to be needing to kind of recognize or kind of spit out again on your external. But just for your purposes of actually understanding the term, what this definition essentially means is just a frame of reference is like a person. You know, I have a frame of reference, you have a frame of reference, so forth. All right. So, the consequences of this is that we can only measure motion relative to an observer, which is what I was talking about before. And secondly, that there is no absolute or motionless reference frame. So there is no kind of starting reference frame or initial reference frame or absolute reference frame. Going back to our car example, the road and earth is not the absolute reference frame, right? Even though kind of to us it might seem like logically, you know, you're driving along the road, so it kind of seems like the earth and the road is the reference frame and you're the one moving, but that's actually not the case. All motion is relative. When you're driving, the road is the one moving relative to you and the car is staying still. Alright, an interesting example of this before I actually quickly move on to the next topic is kind of the classic example of a box, right? Moving through space. If you are in a box with no windows, so you can't see out, right? You don't know if you're the one moving or if the space is moving around you, which is an interesting kind of example of this, right? And in fact, when we get into acceleration and constant velocities, we'll further expand on this example, but we'll wait till we get to that. Next, we're looking at the postulates. So, these are known as Einstein's two postulates if you're ever asked for them in an exam. So Einstein has two postulates for special relativity. The first one is that the laws of physics are the same and can be stated in their simplest form in all inertial frames of reference. So, what this essentially means is that the laws of physics are the same in all frames of reference that are not accelerating. An inertial frame of reference is one that is not changing speed or not changing direction. Or in other words, it's not changing velocity. So an inertial frame of reference could be traveling at 30 meters per second. As long as it is traveling at a constant velocity, it is inertial. If an object is traveling at 30 meters per second in a circle, it is not inertial because even though the speed is constant, the direction is not because it's changing direction. Remember, velocity is a vector quantity, so it's a measure of both magnitude and direction. Right. Einstein's second postulate is that the speed of light, c, is constant in a vacuum independent of the relative motion of the source. So, these two postulates can have some interesting consequences. So, proof of the second postulate was shown by Michelson and Morley's experiment in 1887, and the consequences will be discussed later in classes. And then down the bottom here, we just have the actual QCEE definition snipped out if you want to remember that one. Alright, now getting on to simultaneity. So, events are considered simultaneous. I'm not sure why I just pronounced it so strangely. Simultaneous. Events are considered simultaneous if they occur at the same time. This can be difficult to determine if the events are occurring at distances from each other and the observer, and especially if these distances differ. So, we can say instead that two events are simultaneous if light signals from the events reach an observer who is midway between them at the same time. So this is our definition of when two events are simultaneous. I'm not sure what's going on with my pronunciation. So what this essentially means is that if there are two events, an observer standing directly in the middle between them, if they observe light signals from these two events at the same time, this means that the two events were simultaneous. Right? Now, of course, if our observer is standing at the point of one of the events, even if the two events actually are simultaneous, they're going to observe the light signal from the event they're standing next to way before the light signal from the other event, right? If you're standing next to where a bolt of lightning strikes, you're going to see that bolt of lightning before you see a bolt of lightning that strikes 10 kilometers away, even if they technically occur at exactly the same time. All right. So, consider the train-car example. Say we have a carriage shown on the left, and a light pulse is given from the center of the carriage. So, a light pulse, when it hits the end of the carriage, opens a door at either end. So, if our light pulse emits from the center and hits both of the doors at the same time, then both of the doors opening are going to be simultaneous events. Now, hang on to this example of the train car in your mind, because we're going to be getting onto this later on when we talk about paradoxes. Alright, now let's get on to the speed of light. So the speed of light in a vacuum is a universal constant. And we know that nothing with mass can travel at or faster than the speed of light. So, the speed of light in a vacuum is 2.998 times 10 to the 8 meters per second for our purposes. But typically when you're doing calculations, we're just going to simplify that to 3 times 10 to the 8 meters per second. So there are unusual phenomena that occur when an object with mass approaches the speed of light that explain this. Explain why we can actually never travel at or faster than the speed of light. And these phenomena involve time dilation, length contraction, and the relationship between mass and velocity. So, when we're getting into these phenomena, we're also going to be using them to explain the presence of muons in the atmosphere. And we're also going to be exploring about how Einstein's second postulate about the speed of light, c, being constant in all inertial frames of reference in a vacuum, actually has the consequences of these phenomena that I've just listed out. Right? So as you can see, the content that we've been learning about all kind of interconnects. Alright, so just a quick suggestion. So remember, these terms listed here are mentioned in your syllabus. So if I were you, I would add these into my notes and copy paste the QCEE definition. So remember, you can find those by finding the syllabus online, just by searching Physics QCEE syllabus. Control F the document for all of these terms in the glossary, and then copy paste those definitions into your notes or write them down in your notes. It's really important to do this because in your external, if you're ever asked a multiple choice question on a definition, it will say like, out of these four options, what is the correct definition for time dilation? It's really useful to actually just know the definition off the top of your head, because the correct answer is going to be the answer given in the QCEE glossary. So if you know that answer off the top of your head, then you won't even have to think about like which of the definitions are right or wrong and thinking about it too much. You can just quickly tick off the one that sounds familiar, and then move on to your other questions and spend your time doing things you haven't been able to prepare as well for, such as like, calculation questions, right? Okay, now let's move on. So now we're getting onto the mass effect. So, Newton's second law of motion suggests that as long as there is an unbalanced force, that an object will continue to accelerate. However, we know that the above is not actually always true. How is this so? When we continue to accelerate, when we continue to put an unbalanced force on an object, we're applying a force. At a certain point, it will actually kind of stop accelerating as much, right? So even if we're applying the same amount of force, or kind of, the same amount of, the rate of increase of the force is the same, the acceleration will actually decrease, right? So, as an object gets faster and faster, even if we keep putting more and more force into it, trying to get it to go faster, it will actually kind of lose the ability to go faster. And as we're putting force in, what we see is that the mass of the object actually increases, which is kind of crazy, right? So if you're trying to accelerate an object and it's getting close to the speed of light, as it's getting closer to the speed of light, the energy that you're putting in to accelerate is actually going to not even go towards accelerating it, but actually go towards making its mass bigger, right? So it's going to be accelerating less and getting bigger. Which, yes, again, sounds crazy because it's like, you can't kind of just increase the mass of something by putting more force into it, but this is what we observe. So, what we can tell from this then is that mass is also a relativistic property, which means that mass can be different when observed in different frames of reference. It can be different relative to different observers. It's a relativistic property. So, we therefore have two values, m0, which is the rest mass, or the invariant mass, and this is the same in all reference frames, and m, which is the relativistic mass, and this is the mass in the frame at which the object is moving at velocity v. So, say you have a particle flying around a room, going very, very fast. Say we've captured a muon, right? The rest mass is going to be measured by a person, kind of, say an imaginary, very small person, standing on top of the muon and traveling with it. The relativistic mass is going to be measured by a scientist standing in the room watching the muon whizzing about, because that is the frame in which the object is moving. For the person, the tiny person standing on top of the muon, to them, the object, the muon, is not moving. The muon is staying still, the world around them is moving. Right. So, we actually have a formula for determining the mass effect based on the relative velocity of the object compared to the speed of light. So, as you can see, we have m, or the relativistic mass, is equal to the rest mass m0 divided by the square root of 1 minus the velocity of the object, v squared, divided by c, which is the speed of light, squared. I'll bring that in quickly. This should be a squared up here, not a squared down there. So as you can see, the relativistic mass is always greater than the invariant mass. And this is because when we are dividing here, we are dividing by kind of a number which is making our relativistic mass greater, right? So we are dividing this number here, we're dividing by a small number. So when you're dividing by a small number, you end up with bigger pieces. Think about it like this. If you have a pie and you cut it in half, you end up with big pieces. You're only dividing it by 2. However, if you cut up a pie into 100 pieces, you're dividing by a big number, you're going to end up with tiny, tiny slivers, right? So the bigger the number you're dividing by, the smaller pieces you're going to be left over with, right? The smaller the number you're dividing by, the bigger the pieces you're going to be left over with. So because we're dividing by a small number, we're going to be left over with a bigger number over here. So from this we know relativistic mass is always going to be greater than the rest mass. So the relationship of mass increase as velocity approaches the speed of light is exponential, which I'll show you guys over here. So, as the velocity of the object approaches the speed of light, its mass approaches infinity. As you can see here, its mass is kind of fairly stable, when it's traveling at lower speeds over here. But as we kind of get to around, maybe 0.5, the speed of light, what you can see is that the mass is increasing exponentially. And at c equals 1, this line here, what you can see is that our line actually never gets there. So it's approaching c equals 1 asymptotically, right? It's getting closer and closer and closer there, but it's never actually reaching it. So what you can see from this is as speed increases, more of the force going towards accelerating, the mass is actually going into increasing the mass. So now let's get on to our next topic of phenomena, and this is time dilation. So time dilation is the cause of the moving clocks run slow phenomena. So time is relativistic, i.e., the time interval between two events cannot be the same for two observers that are in motion with respect to one another. So, gravity bends space-time. Therefore, time moves slower in regions of increased mass. The mass of an object will increase significantly as its velocity approaches the speed of light. Hence, its gravity increases and elapsed time slows. Another way to think about this is kind of as a consequence of Einstein's second postulate. So, thinking about the speed of light always being constant for an inertial observer in a vacuum, right? If two observers are seeing the same light, they're going to see that light as traveling at the same speed. However, if those observers are traveling at different speeds themselves, yet they're still seeing the light travel at the same speed, this is going to have consequences on the time experienced by both of those people. So, classic example of this is the light bouncing between mirrors. So say we have a train, right? A person is on the train, and the train is moving in this direction at 0.95 of the speed of light. It's traveling very, very fast. This, of course, is a hypothetical situation. We do these experiments like actually in real life, and of course, we can never get anything that of that significant mass traveling that fast, but we can get them traveling fast enough that with super precise instruments we can actually still measure the differences. But of course, this is just a hypothetical. So this person on the train is observing light bounce between these mirrors. So we have these mirrors and we have light bouncing. Actually, no, make it even a little bit, change this a little bit. Say we have two mirrors and we have light bouncing back and forth between these two mirrors, right? Might even draw that as yellow. So this person is on a train and he is seeing the light bounce back and forth between these two mirrors. Now, say we have a person on the station. He is not moving, he's just standing on the station. And he is looking at this scenario. Alright. To him, he's not just seeing what's happening inside the train, he's also seeing the movement of the train as it's going past. So, instead of seeing just the light bouncing back and forth between those mirrors, what he's seeing is, and I'll just draw it off to the side here, he's seeing the train move as well, right? He's seeing the train moving, and as a result, the mirrors moving. So what he's seeing is the light actually bouncing back and forth like this. Instead of going back and forth over itself, like the red person is seeing, he's actually seeing the light move forwards as well because he's observing the whole train moving forwards. So, now let's think about Einstein's second postulate. So if both of these observers are inertial, say they're also in a vacuum, they're seeing that light move at the same speed. From both of their perspectives, the light is moving at c. Have a think about where this might give us some issues. For the person on the train, the light is moving back and forth this distance here. For the person on the platform, the light is traveling farther, right? Because instead of just going back and forth here, it's actually, and I guess you can prove this mathematically, but I won't go through it now. See, we actually have, this is where the mirror would be that the person on the train is observing. So as you can see, the light is actually traveling along the hypotenuse instead of along this line here, which is what that red person is observing. Remember, the hypotenuse is always the longest side of the triangle. That's proven mathematically. Pythagoras' theorem, right? So the blue person is observing the light travel a longer distance, but he's still observing it travel at the same speed. So what happens as a result is, out of a few other different phenomena, but one of them is happening as a result, is time dilation. Right? So, to make up for this, this person is going to see events occurring in a different time to this person. So, this person is going to experience time normally. This person is going to experience time normally. But when they're looking at each other, they're going to look at each other and go, wow, that person's time is whack. Right? So they don't feel like they're in slow motion or anything, but they're looking at each other and going, wow, that other person's time is just off. Right? If our blue person is looking at our red person, this red person looks like he's in slow motion. Right? It looks like this red person is experiencing time slower. And the reason for that is because we need to allow more time for this light to travel a greater distance in this blue person's perspective. Because they're seeing the light travel a greater distance at the same speed, right? They need to allow more time for that travel to occur. So if they're seeing more time in the carriage, they're also seeing the red person in slow motion. They're seeing everything else happening in the carriage in slow motion, right? But the person on the carriage is not experiencing anything in slow motion. They feel normal. When this red person is looking out to the station, they're seeing the blue person move about faster than normal. So comparatively, he's seeing the blue person move around faster. Even though both of them feel normal within themselves, when they're looking at each other in that different reference frame, they're seeing a difference in time. Alright. Let's move on to our time dilation formula. So, time dilation is maximal when the velocity equals c. So when the velocity equals c, the elapsed time is 0. So at velocity equals c, time stops altogether. Right? It's good that light doesn't actually experience time, nor does it have any mass, which is why light can travel at the speed of light. Right? Alright. Looking at our formula down here, again, this one is on your formula sheet too. We have T0 being proper time, and T being dilated or relativistic time. So proper time is a time measured in the frame in which kind of like the movement is happening. And dilated or relativistic time is the time measured in the frame of the observer. So, if we had a rocket take off, the clock on the rocket would be measuring proper time, and then the clock on Earth would be measuring relativistic time. Alright, now let's get on to length contraction. So this is another one of the phenomena, and we'll go back to our train light mirror example to further explain this as well. So, length contraction is a phenomena wherein the length of an object actually contracts in the direction of motion. So, we have our two values, L0 and L. L0 is the length of those on Earth or not moving, it's the proper length. And L is the length of those moving in the frame of reference, the relativistic or dilated length. So, if we have a rocket traveling from Earth to planet Rigel, then in the frame of Earth or Rigel, the distance traveled is going to be L0, the time is going to be t, and the velocity is v. In the point of view of the people in the spacecraft, the distance traveled will be L, the time for the journey will be t0, and the velocity will be big V. So as you can see, for the spacecraft, if they want to travel the distance and kind of do it in, I guess, relativistically a shorter time frame, they can travel faster. Because if they do that, then the length that they travel will seem shorter, and the time that they travel in will also seem smaller. Right? So, in summary, the relationship between velocity, length contraction, and time dilation is below. This formula is, of course, just coming from velocity equals displacement over time. Length is just displacement here. As you can see, we have a quick diagram on length contraction. As our velocity is increasing, our object is contracting in length in the direction of travel. So as you can see, the height of the shape isn't changing, but because it's going in this direction, it's getting skinnier, right? And then this formula here describes the relativistic length and the length of the, there we go. Alright, now getting on to light as the universal speed limit. So, it should kind of be clear now why light acts as the universal speed limit, and why nothing with mass can travel faster than the speed of light in a vacuum. So, as the object approaches the speed of light, its mass approaches infinity, its length approaches zero, and the elapsed time for a given period approaches zero. So, we have all of these formulas to describe these phenomena, and as a result, nothing with mass can travel at or over the speed of light. There is actually one, I guess, not even exception, but I discussed kind of like interesting fun facts to know, is that there actually is something that can travel faster than the speed of light. and it's nothing with mass. It's not an object. It is actually um, the uh, uh, the meeting of the two blades of scissors, right? If you're closing those scissors, if you close them super fast, that point where they meet can actually travel at faster than the speed of light, which is interesting. But of course, that obviously doesn't have mass. It's just like a point. It's not even like an object or anything like that, like you might describe light as if you're talking about it as a photon. So just something interesting to know. All right. Now getting on to mass energy equivalence. So anything with mass has an equivalent amount of energy. Anything with energy, an equivalent amount of mass. So we can use our formula E equals mc squared to determine the relationship between energy and mass. So the primary consequence of this relationship is that an object at rest has intrinsic energy, or rest energy, that corresponds to its rest mass. And when the object is in motion, its relativistic mass is greater than its invariant mass because there is more energy because it's in motion, right? So this is how we use our mass energy equivalence. We can also use this formula when we are getting into quantum theory, but it just helps us for the moment in determining the relationship between mass and energy. Alright, now we're getting on to the end of our syllabus for special relativity. And we're getting on to the three paradoxes. So, there are three paradoxes you need to be able to explain and describe. So, a typical exam question might just be, explain the twins paradox, right? And you just need to be able to rattle it off the top of your head. So what I'd recommend for learning these is once you understand them, write a short kind of 3-sentence explanation in your own words. Try to make it really concise, and then memorize that on a flashcard. So let's go through the twins paradox. So say we have two identical twins, one of which makes a journey into space in a high-speed rocket. Upon returning, he notices the twin on Earth has aged more. So, consider an application. If inertial reference frames and time dilation, each twin has observed the other in motion. So should have found the other to have aged less, but this is not so. So both of them have been in motion. In both of their perspectives, the other moved away from them and then moved back towards them at a fast speed. Remember, moving clocks tick slower. So both should have observed the other one to have aged less. But what we see is that the twin who went on the spaceship aged less, and the twin on Earth aged more. So, what is the explanation for this? Does this prove a hole in Einstein's theory? Have a think about it. Please pause the recording if you've already learnt this and try to remember the solution. If you haven't learnt this, pause the recording and try to think of the solution. But I'll go to the solution in 3, 2, 1. So, essentially what we have is that one twin goes out in space, comes back, and is younger. The twins were in constant motion relative to another, and both see each other aging quicker. The key is, or the solution, is that only one twin spent the entire time in an inertial reference frame. So the twin on the spaceship actually accelerated away from Earth, then got to the planet, turned back around, so it changed direction. Presumably it slowed when it got to the planet too, and then when it got to Earth it slowed back down to land. So, Einstein's theory only deals with constant motion. It doesn't deal with accelerated frames of reference. That's why in all of our definitions we're talking about inertial frames of reference, which are ones that don't accelerate. In other words, they have a constant speed and constant direction. So, our spaceship twin actually accelerated, right? So have a think about this. Which twin's frame, therefore, measured proper time, and which measured relativistic time? Have a think about it. Alright, getting onto the flashlights on a train paradox. So this is the next paradox you need to know. So, imagine a person on a train in constant motion with a torch. He shines it at a mirror on the other side of the carriage, the distance that the light beam travels. The distance the light beam travels from the frame of reference of someone on an embankment watching the train go by, the light travels a shorter distance. How is this possible, knowing that the light cannot travel faster than c? I'm just going to draw a quick diagram of this. So, for the person on the train, what he's seeing is the light from the torch to the other side of the carriage, right? And the carriage is moving in this direction. Alright, from the perspective of the person on the embankment, what they're seeing is the carriage and they're seeing the back of the carriage move towards the light source, right? So they're seeing this light source, but they're seeing the carriage move towards this light source and the light move towards the carriage. So what they're going to see is the light moving a shorter distance. So, how is this possible, knowing that the light cannot travel faster than c? Pause the recording, see if you can explain it. And the hint is simultaneity. Alright. So, essentially, consider time dilation and simultaneity. The speed of light remains constant, but the events simultaneous to one viewer isn't simultaneous to another. The distance the light had to travel depends on your reference frame. So, the train moving close to the speed of light influences this, even though the person on the embankment and the person in the carriage sees the light hit the end of the carriage at different times. Just because they see a shorter distance, right? Simultaneity is relative based on reference frames. So that is the solution. Alright, now getting on to the last paradox, which is the ladder in a barn paradox. So, for this one here, we have a ladder or a pole, whatever you'd like, parallel to the ground, moving horizontally to the ground at a relativistic speed, or in other words, near the speed of light. So it is undergoing a length contraction and moves through the barn that's length is shorter than the ladder's rest length. So, to a stationary observer, the ladder can fit inside. But to an observed moving with the ladder, there is no length contraction of the ladder, and it is instead the barn that is contracting. Or in other words, the ladder can't fit. Right? Can anyone explain? Let's draw a quick diagram of what's occurring here. So, we have from a person watching, from their perspective, we see a barn, and we see the person running in with a ladder shorter than the barn because they are moving at a relativistic speed, say 0.9 c. So the person outside is seeing the ladder being contracted to be shorter in the direction of motion. However, in the person who's running's perspective, what they see is the barn contracting and their ladder being the same length. I'll just quickly draw. See the rungs are close together here, but for the person running, what they're seeing is the ladder not contracted, and they're seeing the barn being contracted. Right? So how can the ladder fit inside? The observer sees the ladder fit inside, but from this person's frame of reference, the ladder is never going to fit inside because it's too long. So, who's right? What is the solution? Right? How can it be that in this person's frame of reference, the ladder fits in, but in this person's frame of reference, it doesn't? Does it fit or does it not fit? What's the answer? Alright. The solution is that simultaneity is relative. So just because two events are simultaneous as measured from one frame of reference, it does not mean that they are simultaneous from another frame of reference. So, the doors being opened and closed are not simultaneous events from the frame of reference of the pole. So, going back to our diagram, if we have a door at either end of these barns, right? And then, so in this person's frame of reference, the person running in can fit in with both of the doors closed at the same time. From the frame of reference of the person running, the doors cannot close on either end simultaneously. But the doors closing can be simultaneous in one frame without being simultaneous in the other. It's all relative. Remember? So on this person's frame, what actually they see is they see this door opening. Then while they're inside the barn, right, this door is opening, right? So the doors opening and closing are not simultaneous. The door closest to them is opening first, and then the door furthest from them is opening second, and then this door is closing again behind them, and then this door is closing behind them. So the doors opening and closing are not simultaneous events, even though they are in the frame of the person watching. Alright, now let's get on to our next topic today, which is on quantum theory. So, here we have a snip of the syllabus on quantum theory. So, the main things that you need to be able to do is you need to be able to explain light as a wave and light as a particle. You need to be able to explain the differing evidence for light being a wave and light being a particle. And then you also need to be able to explain the two models of the atom that we're looking at, which is the Rutherford model and then the later and improved Bohr model of the atom. And you need to be able to explain like why they're better, what limitations the Bohr model addressed, and so forth. So, getting onto light. What we've essentially seen in the past few 100, 200 years or so is that when we conduct experiments using light, sometimes light behaves as a particle and sometimes light behaves as a wave. And while initially we kind of thought that, some people were doing the experiments wrong, they were invalid for some reason, what we eventually came to realize was that light actually can behave as both a wave and a particle. So, what we can actually do is talk about the wave-particle duality of light, where in some cases it behaves as a wave and in some cases it behaves as a particle. So, in Year 12 Physics, we go over a few examples, some or experimental evidence, some showing that light is a wave, some showing that light is a particle. The first of these that we go through is Young's double slit experiment. So, in Young's double slit experiment, what our scientist Young did is he had a sheet, he cut two slits in it, and then he had a screen behind the sheet. This is what we can see here. We have the two slits and the screen behind the sheet. So, he shone light at the two slits and saw what he observed on the screen behind it. So, if light behaved as a particle, what we would expect is these two big blobs of particles behind the slit. It would kind of be like if you were, I'm not sure, like shooting a paintball gun through two big slits, right? You're not going to see particles over, you're not going to see paintball splatters over here or over here. You're just going to see big splatters behind the two slits, right? However, he observed something different. What he actually observed was a pattern, right? Where we kind of had bigger splotches over here, getting smaller and smaller on either side. And this is consistent with light being a wave because we observed constructive and destructive interference patterns. So, this is a visual of what you can see. You can do Young's experiment very easily on your own. We have a bigger splotch here and then it getting smaller and smaller symmetrically on either side. So, the waves of light interfere, making bright spots, and they interfere constructively yielding bright spots or destructively yielding dark spots. So, Young's double slit experiment showed that light was a wave because the light exhibited constructive and destructive interference patterns, which is a property of waves. You would have gone through this in more detail at the end of year 11 if it feels a little bit familiar to you, but don't stress too much if you have forgotten a lot of it. The next thing you need to be able to understand is the wave model of light. So, the characteristics of electromagnetic radiation are that they consist of oscillating electric and magnetic fields. Oscillating means going back and forth, right? So we have electric and magnetic fields going back and forth. These two fields are at right angles to one another. And the speed of the wave is dependent on the magnetic and electric properties that it is traveling in. So the speed of light differs in different substances, which is called the refractive index. So of course, if you have a denser substance, there's going to be more resistance to the light, so it's going to take longer to travel. This is, an example of why on our Earth, right, when it's a sunny day, the air is warm. It's because the light is hitting the air particles and giving energy to the air particles, right? But in space, even though there's lots of light, right, because there's lots of light traveling through, it's a vacuum. So there's no particles for the light to actually hit, and nothing for the, to absorb that energy. So that's why it's so cold out there, right? Another example would be if you have a window facing the sun. Say you have a thick window. If you put your hand on the window, it might be quite hot, and that's because the light is hitting the window, and because the window is so dense, a lot of the energy is being given to the particles in the window and slowing that light down. Again, this is also why when we're talking about the speed of light, we usually refer to the speed of light in a vacuum, and that's because there's nothing to kind of interfere with the speed, right? Whereas if it's, just on Earth in general, the density of the air and, all this kind of stuff impacts the speed. And of course, because there's more stuff there, the speed of light is slower in the atmosphere than it is in a vacuum. All right. Now, these two oscillating fields are perpendicular to the direction of propagation. So as you can see, our wave is going in this direction, but our two fields are going up or across, right? Perpendicular to the direction. So this is the main thing that you need to remember about the wave model of light. The other formula that you need to remember is that the energy is equal to hf, where little h is Planck's constant. This number is in your formula sheet, so don't worry about remembering it. And f is the frequency of the light in hertz. Now getting on to blackbody radiation. So blackbody radiation provides evidence for the particle model of light, right? So blackbody radiation occurs when we have a black metal object that emits energy from within itself. And it does not reflect any light. So if you're giving it energy, it's not going to reflect any of it, it's just going to absorb all of it. Of course, there's no such thing as a perfect blackbody, but we can get pretty close. So, what we can see on the graph down below is the distribution between intensity and frequency. So as the frequency increases for the first part, the intensity increases, then as the sorry, this is the wavelength. As the wavelength increases, the intensity increases. As the wavelength decreases on this side, the intensity, so, hold on, I'm confusing myself. As the wavelength increases for this first part, the intensity increases. Then, as the wavelength gets even bigger, the intensity decreases. And obviously, these temperatures shown here, right? For the higher temperatures, we're going to have higher intensities. So, how did this show that light was a particle? So, the explanation of this kind of eluded scientists until a famous scientist, Max Planck, proposed that the energy emitted by black bodies was from the vibration of atoms limited to certain frequencies that were multiples of some value. So, light in this situation is emitted as packets or quanta. So the frequency of light emitted by the vibration of an atom is proportional to the change in energy of the atom, related by Planck's constant. So this is proof that light exists as a quanta. Alright, so the concept of black body radiation and how it shows that light exists as a particle rather than a wave actually gets a little bit complicated the more you dive into it, kind of unlike the two other experiments that we look at, right? So what we have on the slide here is really enough, it's all that you need to know. If it seems a little bit confusing, that's because it is. When we get into Young's double slit experiment and then for the photoelectric effect, it's more easily understandable and you can go into more depth on them. The formulas that we have to describe black body radiation are E equals HF, C equals the wavelength multiplied by frequency, and then combining those two previous equations together, we get the energy is equal to hc over the wavelength. Alright. We also have Wien's displacement law, and this describes the relationship between the temperature and the peak wavelength of black body radiation curves. And this is given by the wavelength is equal to B, Wien's displacement constant, over the temperature in kelvins. Make sure that you remember that this temperature is in kelvins. It's really easy to be given a temperature in degrees Celsius and then forget to change it around. So, if you're ever asked to find the peak wavelength of the black body radiation curve, you can apply this formula here. Alrighty, so here we have a nice breakdown of all of the equations that you're going to need to be able to understand for quantum. So, remember the energy of a single quanta of light of frequency f is given by E equals hf, where h is Planck's constant, and that, remember, is in your formula sheet. The frequency and wavelength of light is related to its velocity c by the wave equation. That middle one isn't actually given to you on your formula sheet, but you are given v equals wavelength times frequency. So if you're having trouble remembering it, you can just remember that the velocity of light is c. So you can just sub in c for v. And then combining those two equations, we can get that the energy is equal to hc on the wavelength. Alright. So this is kind of a visual representation of the photon model of light, right? So, the photon model or particle model of light deals with the particular light behavior we observe of subatomic particles. So, light exists as numerous particles which we call photons, and photons have no rest energy, they have no mass, and they have kinetic energy. So the energy of the photons can be described by E equals mc squared. Now the last kind of experimental evidence that we learn about when we're looking at the model of light is the photoelectric effect. So this one is particularly interesting. So the photoelectric effect provides evidence for the particle model of light. So, when a metal surface is illuminated by electromagnetic radiation, essentially light, remember light is electromagnetic radiation, of a high frequency, electrons are ejected from the metal surface as a photocurrent. This ejection only occurs if the frequency exceeds the ejection frequency F0. The ejection frequency differs depending on the metal. So, essentially what we have so far is we have a metal surface, right? We have light being shone at this metal surface. If the frequency of the light is high enough, then the light is actually going to detach electrons from the metal, and these electrons are going to run around our electrical circuit to create a current, which we call photocurrent. However, if our frequency of the light is too low, then no electrons will be ejected. So, we observe some things about this experiment. Firstly, when a photocurrent is registered, increasing the intensity of light will increase the magnitude of photocurrent. So, the intensity is essentially how bright the light is, how much light there is. A good example of this would be if you are standing next to a street light, there'll be a greater intensity closer to the street light than farther away, because farther away the light has dissipated more, it's not as bright, right? So, when the intensity is increased, when there's more light, it increases the magnitude of photocurrent. And then when we increase the frequency of the light after the ejection frequency, so once we've already got the electrons being ejected, if we still increase the frequency after that, that will increase the kinetic energy of the ejected electrons. Alright? So, increasing the intensity increases how many electrons there are. Increasing the frequency increases how much energy those electrons have. So, you can have a low intensity light with a high frequency that will eject not very many electrons, but all of these electrons will have a lot of energy. Similarly, you can have a high intensity light with a low frequency that will eject a lot of electrons, but none of these electrons will have a lot of energy. And then, of course, before we have reached our ejection frequency, it does not matter how intense the light is, no electrons will be emitted if we haven't reached the ejection frequency or the threshold frequency. Right? And then down there we just have a visualization. So we have the red light going in and ejecting the electrons from the metal. So, how does this prove that light is a particle? And why do we see all of this stuff occurring with the ejection frequency and the intensity of the light? Right? This is a little bit strange. What is the reason? So, this phenomena cannot be explained by the standard wave model of light. It can only be explained by the particle model. And this is because the only explanation is that a single photon ejects a single electron, giving all of its energy to the electron or none of it. So, think about it like this. If we had waves coming in, then the transfer of energy from waves would be continuous, right? Kind of the waves are coming in and giving more and more energy to the metal, and the longer the waves have been there, the more the energy will build up. So eventually, even if there is a low frequency, if there's a higher intensity, eventually that energy will build up and the electrons will jump off, right? However, that is not what we see. What we actually see is that the energy of the electrons is equal to the energy given by the frequency minus the energy required for the electron to actually just jump out of the metal straight up, right? So what's actually happening is we have lots of little photons coming in here, and each of these photons gives energy to each of the electrons, but only one. Each photon gives all of its energy, or none of its energy, to each electron. The photon can't give some of its energy to one electron and some of its energy to another. No. All of its energy or none of its energy. Right? So, this makes sense then, right? Because if we have a higher frequency, our photons will have more energy and thus be able to give more energy to the electrons to bounce off. And if we have a higher intensity, we have a greater number of photons coming in. So if we have more photons, we have more photons to give energy to electrons, right? If we have 1,000,000 photons, then 1,000,000 electrons can jump off the metal. However, even if we have a high intensity, we have lots of photons, but they don't have enough energy in themselves, still no electrons will be ejected because all of our photons are coming in, giving energy to lots of electrons, but they're not giving them enough energy. So what's happening is the electrons might be able to get a little bit farther away from the atom that they are orbiting, right? They might be able to jump up an energy state, which we'll get into when we get into standard model and quantum and the rest of quantum, but not quite enough to actually ionize the atom altogether and jump completely out of the atom, right? Only enough to maybe get it an energy state or two up away from the nucleus. All right. So, 3 forms of energy in the system can be defined. So the first is the energy of the photon, which is given by E equals hf. The second is the energy of the electron binding to the metal, which we call W, or the work function, which is given by H multiplied by the threshold or ejection frequency. Then we have the maximum kinetic energy of the ejected electrons. So, our maximum kinetic energy is going to be however much energy the electron was given minus however much it took for it to just jump out of the metal, and that's what it's going to be left over with. And this gives us the maximum kinetic energy of the electron. The other thing that you need to be able to understand about the photoelectric effect is the cutoff voltage, or the stopping potential. So, what we can do is we can actually measure the photocurrent with a negatively charged collector plate. So, what we do here is the negative potential actually reflects the incident electrons, and eventually this potential becomes large enough to deflect the entire photocurrent, right? So the voltage that this happens at is actually called the cutoff voltage or the stopping potential. Thus, the kinetic energy of the ejected electrons can also be determined by using our formula for kinetic energy, half mv squared, right? And this is going to be equal to our maximum kinetic energy and our cutoff voltage, right? Okay, now we're getting on to Rutherford and Bohr's model of the atom, which is our last part of quantum theory. So, Rutherford's model was the early model of the atom, not the earliest, but one of the early ones. And it's kind of the stereotypical model of the atom. So it describes the atom as mostly empty space with a positively charged nucleus set in space with negatively charged electrons orbiting around it. Right? So there are actually limitations of Rutherford's model, reasons why it isn't so great. The main one is that Rutherford's model predicted that atoms would be super unstable, right? It predicted that atoms would actually collapse on within themselves, right? The reason that it did this is because we know that our electrons are moving around kind of in circular or ellipsoid orbits, right? But they're changing direction, which means they're accelerating. And we know that accelerating electrons lose energy. So if these electrons are kind of constantly accelerating, constantly kind of like hemorrhaging energy, they're going to have less and less energy to kind of overcome the forces holding them to the nucleus. So as a result, they're going to collapse in to the nucleus. So Rutherford's model predicted that our electrons would just kind of be like spiraling in towards the nucleus constantly, and all of the atoms around us would be super unstable, which isn't really what we observe, right? So, the other issue with his model was that he didn't specify where the electrons were. And this is addressed by Bohr's model. Another thing that we'll get into with Rutherford's model and its limitations is actually the emission and absorption spectra as well. So because Rutherford didn't specify where the electrons were, when electrons were losing or gaining energy, it kind of predicted that electrons could lose or gain any amount of energy at all, because they could be anywhere within the atom. However, what we actually observed was that electrons could only emit and absorb certain amounts of energy, not just kind of like any amount at all. It would be a certain amount, right? And this is when we get into emission and absorption spectra, which we'll get into later. So that was kind of the other limitation with Rutherford's model. Now let's get into the Bohr model. So Bohr proposed that electrons only radiate energy in exact quanta or definite amounts of energy. And so as electrons radiate energy, they move inward towards the nucleus in definite quantum orbitals until a stable orbital is reached. So given this information, I'd like you guys to pause the recording and have a think about how the Bohr model addresses the issues of the Rutherford model. Right? Pause the recording, have a think about it, try to remember it from your notes, or try to kind of guess if you haven't learned this in class yet. So, let's talk about how it addresses the issues. Firstly, if each electron releases or absorbs a certain amount of energy every time it moves, and it kind of releases energy continuously, not continuously, it releases energy in discrete amounts until it reaches a stable orbital. This tells us that we have kind of distinct, discrete orbitals, whereas Rutherford's model just kind of said that we had electrons going around anywhere. Bohr's model tells us that we have discrete orbitals that electrons can be in, but they can't be in between. So, if we have an electron moving down an orbital, it's going to emit energy because it's losing energy, right? And because the electron has moved down a certain amount, it's going to emit a certain amount of energy, which is relative to the difference in energy between the orbitals, right? So the absorption of a photon with energy equal to the difference in energy between an electron's stationary state and excitation energy state will cause the incident electron to move to the excitation state. So if we give an electron a photon that has the energy that it needs to move up an energy state or move up an orbital, it will. Every change in electron orbit corresponds to the absorption or emission of electromagnetic radiation. So absorption is when it moves up an orbital, or emission is when it moves down an orbital. So if the electromagnetic radiation is high enough energy, it will knock off the electron ionizing the atom. So the limit is the ionizing energy, right? So if we give an electron a bunch of energy, it will have enough energy to actually jump out of the atom altogether. And this is what we saw with the photoelectric effect, right? We saw if we gave the electrons enough energy, they would just jump off the atoms altogether and create a photocurrent. All right, so now let's get into the emission and absorption spectra, which is what I was talking about before. So, as I said, the Bohr model tells us that the orbitals of electrons cause the emission and absorption of photons of definite and specific energy levels. And we know that this is related to the frequency of the light emitted or absorbed. So, the emission of energy in jump back down orbitals is stepwise, which means it occurs in chunks, right? A way to visualize this is being on a bookshelf. If each shelf is an energy state, a book can never be in between shelves. It can either be on one shelf or on another shelf, right? So, we can see the frequency of light emitted and absorbed if we run it through a prism spectrometer. And what we see is that the absorption and emission values are equal and opposite. So, the frequencies of light that a electron will emit are opposite to the frequencies of light which an electron will absorb. However, Rutherford's model predicted a continuous spectrum, right, where any frequency was emitted or absorbed. But of course, this is not what we saw. We saw discrete and definite amounts. All right, getting on to the Balmer series. So Balmer determined the mathematical relationship between the light colors emitted by excited hydrogen gas atoms. So we have a formula for determining the relationship between the wavelength and the number, the final and initial number. So Bohr determined the orbits for the hydrogen atom electrons based on the wavelengths for the spectral lines. Right? So, We also have de Broglie's justification of the Bohr model. Um, so this applied the theory of wave-particle duality to the Bohr model of the atom, and this allowed the explanation of why only certain orbits are facilitated in the atom. So the circumference of the orbit must be an integral multiple of the electron wavelength. What this essentially means is it must be a whole number, remember, an integral is a whole number. So this gives the below formula, n times wavelength equals 2 pi r. So remember the 2 pi r, just like from regular maths, is equal to circumference. So n must be an integral, or like a whole positive number. And then the electron wavelength is given by our symbol there. So of course we have an integral multiple of the wavelength is equal to the circumference 2 pi r. Alright, so something as well that you can take from this, and this is also one of the principles of Bohr's model, although I guess it's not something that we typically focus on a lot because the concepts we don't learn about too much in year 12, but that is that the angular velocity of the electrons is discrete, right? So this is a little bit of what de Broglie was talking about here. Okay. With all of that being said, that is our content done for today. So, what I'm going to do now is I'm going to take you guys through some final study tips that I have. As I said, I graduated in 2021. So I'm just going to go through some tips that I have specifically for physics and potentially for kind of managing all of your other subjects at the same time. So, firstly, make sure that you work up to doing practice questions and homework in exam conditions, so you're not always flipping back to your notes. Maybe you're even timing yourself. If you find that you get a little bit nervous or stressed when you're being timed, it might be a good idea to practice doing that. Make sure you're using your formula sheet. A really good idea is to print out your QCEE formula sheet if you can, and practice using that so you know where all the formulas are, you're familiar with all of them, you know where all of the constant values are, such as Planck's constant, Wien's constant, and so forth. You're all familiar with that, you know where everything is, you understand how to do all of the conversions, so make sure you're practicing with your formula sheet, and make sure you're practicing with your graphics calculator so you're not getting confused on the day. And you're not doing it kind of on your laptop or on a different calculator or on Desmos or something like that, right? And really do make sure that you are doing practice questions for all of the topics, right? The best way to kind of practice or, learn the content is to kind of practice it, right? Next, spaced retrieval will save you. So make sure when you're learning your definitions and your concepts that certain periods after your lesson, whether it's at school or at ShootSmart, or a video that you watched or anything like that, make sure that you are using flashcards or kind of asking yourself questions about the content and remembering it from your own mind. And you need to do that in intervals. So you need to do it, I'm not sure the science is, but maybe like 3 or so times after you learn the content. And this really helps to for your brain to remember it. Otherwise, it is very easy to forget. Alright, mark all your work. It's impossible to know if you're making mistakes if you're not marking it. And then really clearly make a list of mistakes that you commonly make. So this is something that I had on my notes for my external. If there was a mistake that I commonly made or something that I just wanted to be wary of not making, an example of this relevant to today's content is E equals mc squared. I would always forget to square the c for some reason. So I made a note to myself to always remember to square the c. So when I was in my exam and when I was practicing, whenever I was using E equals mc squared, I would always make sure that I had squared it and really double check with that in my mind to make sure that I wasn't making that mistake. Get some variety in your notes. You can use things from multiple sources, but try to keep it focused. Don't have all of this like miscellaneous stuff. So you can use your textbook, online sources, YouTube videos, this lecture, anything that you'd like. But try to make sure you have a decent understanding of the content too. Something that really is useful when you're kind of making your notes, like your class notes and also like your external notes, is to make sure that you are A, writing things in your own words, right? I think the only reason that I was able to understand a lot of these concepts so well was that I would write all of my notes in my own words. If I copied something from class, I'd go back to it later on when I was studying, even if it was a few months later, and make sure that I understood it and wrote it all in my own words. And the other thing is I focused on making my studying efficient, right? So I guess instead of kind of studying really, really hard and like getting into the exam and being stressed about it and like just worrying that I wasn't including enough detail or anything like that, I kept it very focused. So in my notes, I would only have exactly what the syllabus asked for, and I practiced a lot of exams, past exams, previous externals, practice exams, so forth, to make sure that I really had everything down. I'd practiced a lot, and I wasn't kind of learning things unnecessarily and kind of clogging my brain up, because of course you have like 5 or 6 externals, so you really want to make sure that you're not doing more than you need to be doing. Again, take mocks seriously. Don't go crazy with it. It's a marathon, not a sprint, but do take them seriously. They're a good indicator of how you're going, and a really good test in like in an authentic setting to really tell you like how much work you need to do. So, again, make a glossary. You have a lot of definitions to know for physics. Use the QCEE definitions, not your textbook definitions. I've said this before. So again, control F the syllabus document to find those definitions and memorize those. It's really easy marks to kind of memorize those definitions. If you kind of get them over and done with, in your exam, you can just do them without a second thought at all in like 2 seconds, and you can spend your time on other things. It's not even necessarily about, I guess, understanding the content for those definitions. It's just about knowing that exact wording, right? Next, steal some friends and make a study group, and really practice on doing it all together. It's really helpful when you can, for yourself and for others, obviously, if you can help other people do questions. A lot of the time, if you're explaining a concept or something, or explaining how to do something to somebody else, it really helps your own understanding. And a lot of the time, somebody else will ask you questions that will point out gaps in your own knowledge, where you can go to your teacher or back to your textbook or something like that to kind of fill that in. And then, of course, make sure you know how to use your calculator, please. Especially with your graphics calculator. On your external, you're going to get a lot of questions. A lot of questions where you need to kind of graph things, or you're looking at gradients or stuff like that. So really, especially if you're in general and you're not used to using a graphics calculator, um, go through the past external exams and practice using your graphics calculator the most efficiently for those questions. Because yeah, you'll get a lot of questions with graphs where you need to figure out graphs, where you need to find intercepts, where you need to find gradients, all that kind of stuff. Do some regular study, even on the holidays, but make sure you rest. Again, don't overdo it. What I'd recommend is kind of doing maybe like 20 minutes a day. Really is like enough. You could even do less and still really benefit from it. Um, and yeah, don't stress yourself out too much. The best thing that I ever figured out, and I didn't do this intentionally, but it really was helpful for me in year 12 and in any of my further academic pursuits at uni, is to, once you've nailed the basics, practice the hard questions. Like, do not just sit around and kind of slog through easy questions. That's really boring. That's just really, really boring. And you learn the most when you're doing harder questions. So push yourself. If you push yourself and you do harder questions, you're learning more, and you also don't need to spend as much time studying because you're studying more efficiently. And because you've been putting more effort in to doing those hard questions than you would have otherwise if you were doing easy questions, you'll be expending more effort. So you'll deserve the rest more. So make sure that you're practicing complex questions regularly. um, that really is my best tip, honestly. That's especially what I would do in maths. Probably because I was more prepared for maths than for physics. But I would just kind of sit down if I had a spare moment, and I wasn't like, just like relaxing and enjoying myself. I would just kind of, you know, scour through my textbook and find like a hard question and just see if I could do it. I might sit there for like half an hour, just kind of like thinking of a million different ways that I could do it until I could figure it out. Maybe you don't have that level of nerdiness, but if you even have a little bit of that, I'd really recommend. All right, my next not tip. My next tip is to be friends with your teacher or a different teacher if yours is an A1. I know it's really difficult if your teacher kind of is not as interested in teaching you, if they kind of have other things to be doing. It's really difficult to kind of understand the concepts and really to feel motivated to study at all. So if your teacher doesn't really gel with you, try to find a different teacher to be friends with to really help, even if it's just, somebody that that knows a lot about physics, maybe like, your grandparent or, a family friend or something like that. Seek help and clarification, ask other people in your class, ask your teacher. Keep a note if it distracts you during your study or if you forget. And then break down the formula sheet without using your notes or looking anything up. That's especially helpful for the electromagnetism topic because you have so many formulas. It's really easy to forget like which formula is for which thing. What's for a solenoid? What's for a straight wire? What's just for a particle? That kind of thing. So break it down without using any notes or anything because obviously when you get your formula sheet in your exam, it's going to be brand new. Nothing written on it. Right? All right. With that being said, I'm just going to go through a quick review of the content that we went through today. So, for special relativity, we went through Einstein's postulates, we went through time dilation, length contraction, change in mass, mass energy equivalence, and the paradoxes. Then in quantum theory, we went through Young's double slit experiment, black body radiation, the photoelectric effect, and Rutherford and Bohr's model. And then just a few reminders: make sure you study consistently for your externals, don't stress too much, do lots of practice, check your answers, and do all of the past exams on the QCEE website. Make sure you're doing difficult questions, and overall, don't stress. It's year 12, it's not the end of your life. Just kind of study consistently, practice some difficult questions, and I can guarantee you will be a-okay. Alrighty. Good luck with your externals and any further assessment, and thank you for listening. Alright, have a good day.